Let's look at outliers in the data. Think about shopping online. You add something to your cart, proceed to checkout, and fill out the payment information to complete the transaction. Perhaps you use your credit card to make the purchase, and the whole process can be done within seconds. There's a chance, however, that someone else may have stolen your credit card information and pretend to be you when making those purchases. Credit card fraud detection has become very important in today's e-commerce. How can we detect frauds without seeing the consumers or criminals face to face? The key is how we can differentiate suspicious transactions from normal activities. What is normal? What is abnormal? In terms of data science, what are the anomalies or outliers? Imagine if the normal data are those generated by a particular data model or process. An outlier is a data instance that deviates significantly from the rest of data, something that must have been generated by a different model or process. Think about the credit card transaction again. You, the person, is a model or process responsible for the normal transactions. The fraud transactions, however, do not come from you. The criminals generate them. The normal data and abnormal data, or outliers, may appear in the same data set, just like real and fraud transactions appear in the same monthly bill that you receive, but they come from different models. Outliers are to be distinguished from noise. And there is an important distinction here. Noise, by definition, is a random error or variance in a major variable and is an inherent part of normal data. Noise comes from the same process that generates the data. It is there because of the randomness in the process or model. Using the credit card example, noise may come from situations when you make a bigger purchase than usual, or when you travel to another place or shop in a location far from home. But they are still the purchase that you make, not something due to criminal activities. To understand what noise is and where it comes from, let's look at an example. A normal spender, just like you. Think about the amount of money that you spend on an ordinary purchase online. Perhaps on average you purchase $20 for each order with a deviation of $10. So we can set the mean value mu and the standard deviation sigma to 20 and 10 respectively. Assume your purchase behavior follows a normal distribution. And so we can build a normal distribution model using your mean and deviation and use it to simulate 100 purchases. Here we use the NumPy's normal distribution model to generate the 100 purchases, just like what you could have done. Now we show the distribution of the generated data, the 100 purchase amounts from the normal distribution. Because we assume the data follow a normal distribution, and they do, the data should follow the normal distribution curve. So let's compare the histogram to the normal model that generates the data. The blue curve depicts the model, the normal distribution where data come from. But it is easy to tell that the actual data shown as the histogram do not form the exact bell shape of the model. The actual spending, for example, may tend to have more purchases with a greater amount than what the model suggests. This is because the model is probabilistic, it's a random process, and it comes with a degree of randomness. This leads to the variance in the data and some degree of unpredictability of individual data instances. And this is the noise that we talked about, which may appear to be outliers, but in fact comes from the same model that generates all data here. Just like you may make unusual purchases, but those purchases still come from you. They are just part of the noise. They are not outliers. There are several types of outliers. A global outlier, or a point anomaly, is a data instance that significantly deviates from the rest. This is about an individual outlier on its own, regardless of the condition or context. So a fraud transaction is an outlier regardless of how you look at that transaction. A contextual outlier or conditional outlier is a data instance that deviates significantly in a specific context. Now, such an outlier may look totally normal globally when you put it alongside with all other data. But they are abnormal in certain conditions or contexts, and the context is defined by other attributes. For example, a temperature of 32 Fahrenheit may look totally normal. But if you observe such a temperature in the summertime of Florida, it becomes something really unusual, and it is an outlier. Collective outliers are a subset of data instances collectively deviate significantly from the whole data set. Now, these are collective outliers as a group, even if the individual data instances may not be outliers. So it's a behavior of a group. Oftentimes, they can be also multiple groups of outliers in the context of other data and their relations to other data points. So these are the basic types of outliers. The main takeaway here is that they come from a different process than that generates normal data, and we should look at an example to see how this is the case. So this is a very classic example about the number of international phone calls from Belgium during 1950 through 1973. Now the number of phone calls are in millions. So when we load the data set, we can take a look at the data. There are the years and the number of calls in millions for each individual year. We can take a look at the basic statistics of the data, the mean, the standard deviation, the quartiles, and so forth. We can plot the distribution of the number of phone calls. We can look at the potential correlation between the year and the number of calls. And indeed, you can see that from here, there is some positive correlation between the year and calls. And looks like over the years, the number of phone calls from Belgium did increase. So given this correlation, perhaps we can build a linear regression model so that we can use the year to predict the number of phone calls, for example. We can use the least mean square model, which is very common, and it tries to minimize the mean square errors. And essentially what it does is to fit all the values and try to minimize the error altogether. So if we conduct a linear regression based on the classic method of least squares, which is to minimize the mean square errors, we can obtain this regression line, which depicts the relation between the year and the number of phone calls from Belgium during that period. The linear regression model shows the positive relation between year and the number of phone calls. Over time, looks like there is an increasing number of calls from Belgium, which makes sense. Again, the regression model here is to minimize the mean square errors. As a result, the model tries to fit the regression line along the mean values over the years. And so here every data point matters in the model. An alternative regression technique is referred to as a quantile regression, which is part of a family of techniques for robust regression. We note that the quantile at 0.5 or 50% is the middle of all values and is in fact the median. So a quantile regression with Q equal to 0.5 is essentially median regression based on least absolute deviation. In this case, when fitting the model, values and errors in the middle have a greater impact on the regression model. Extreme values, which are at the two ends of a distribution, will hardly have any impact on the median, and they do not affect the outcome. So outliers will be less likely to impact the results. So this is the idea of the robust linear regression, and here is the median regression, so to speak. And so if we use the median regression, we can also create a model with the regression line, which is shown as a blue line here, and we can compare the regression line of the median regression to the regression line based on the least square errors that we used earlier, which is depicted as the red line. The two lines are very different. In particular, the least mean square model has a much steep regression line. So what happened here? Now if we plot the actual data, the figure does give us some clues about what makes the difference. As shown in the data, there are anomalies in the data, specifically during years 1964 to 1969, where the number of calls appeared to be unusually greater than the other years. The model based on the least mean squares, the red line, is fitting the regression line in terms of mean square errors. The mean, as we know, is affected by all values. So essentially, the least mean square model is trying to please every single data point, and the group of outliers will also have a major impact on the final regression line, which goes in between the normal data points and the outliers, the red line. The median regression, so to speak, the blue line, is immune to the outliers because it relies on the median deviation. As you can see, it fits the normal data points very well. But what are the outliers? What do they represent here? Where do they come from in this data set? In our definition of outliers, we declare that they must have come from a process or model different from the one that generates the normal data. So if the normal data points come from the number of phone calls Belgian people make, what are the outliers? Who make those phone calls? Or from what different process do the number of phone calls come from? It turns out that the outliers are still about phone calls from people in Belgium during that period of time. However, they were mistakenly recorded as the number of minutes instead of counts of individual calls. So while the black normal data points come from a counting process, the red outliers come from the time log. They are indeed two separate models. So in the Belgian phone calls example, the outliers show a clear departure from the normal data points. These can be observed through visualization and detected or alleviated by methods such as robust linear regression. This serves as an example where the distinction is clear and outliers are easy to detect. In many other real-world applications, however, the distinction between normal data and outliers may not be a clear cut. We may not be able to draw a clear border between the two. There is often a gray area, and it is hard to tell what is normal and what is abnormal in the data. And when we discuss outliers as some form of departure from normal data, it requires a measurement of the departure. Technically, we need to choose a specific similarity or distance measure so that such a departure can be quantified. There have been many useful measures that we can potentially use. The bad news is the effectiveness of these measures is domain dependent, and none of these are universally applicable. We mentioned earlier that outliers are different from noise, which is due to data variance and comes from the same random process that generates normal data. The distinction between outliers and noise is an important one. However, to distinguish them properly in the actual data is a very difficult task. In certain variables or dimensions, data values of outliers and noise may have overlapped, creating outliers or noise in disguise. Finally, what is the purpose of detecting outliers? What do outliers mean and imply in a particular domain application? These are questions relevant to specific problems you try to attack with data mining. Understanding them and their implications is very important.